Alright, so this video is just going to provide a bunch of practice problems covering some of the early alkene addition reactions that you learn in organic chemistry. It's going to cover acid catalyzed hydration, oxymercuration, and hydroboration. So different ways to turn an alkene into an alcohol. Let's get it. What happens when you take this alkene and treat it with water and a strong acid? Um, Feel free to pause and figure out an answer, and I'll let you know in a sec. So it turns out what you get when you run this under a hydration reaction, you end up with this alcohol, which could be surprising because the OH group is not adjacent to where the double bond was originally. So situations like this, it can always be helpful to draw a mechanism to figure out um, why the reaction played out this way. So let's try that. Okay, so whenever you see water in solution with a strong acid like H2SO4, just assume the acid completely protonates the water. So pretty much all you have in there is a bunch of hydronium ions. So following the mechanism, this is going to take a hydrogen off of this positively charged ion and form a cation where the double bond was before. Notice the ion goes to the more positive, the more substituted side, following Markovnikov's rule. Okay, so now we have a carbocation and water in our solution. Um, but how does the water bond on the left side as opposed to the right? What we have here is we have a hydride shift, where a hydrogen moves over to stabilize the charge on an even more substituted carbocation. Okay, then let's finish this out. And then finally, it's deprotonated by another molecule of H2O. And there is your final answer. But now, what if we change the reagents? We take the same starting material and run it through in oxymercuration to mercuration. Uh, Run through this yourself, see what you get, and then I'll check back with you in a sec. Okay, so this time we get another alcohol, but it's slightly different, where there is no rearrangement. You might understand why, but if not, we can still go through the mechanism right now. This is mercury acetate. The OAC just stands for acetic acid. So it's a mercury atom bonded to two acetic acids, and it has one leftover lone pair. What we do is we can bump some electrons around. This acetate can come off, leaving this with a pretty positive charge, but at the same time, we create mercurium ion by kind of split sharing the lone pair with the free lone pair and the double bond in one step. And then we get this almost triangular ion with an acetic acid hanging off. Here, let me move this up. Okay, so this is what you end up with. The important thing about this is that there's no carbocation formed. The cation's on the mercury. Whenever there's a carbocation, we can have rearrangements. So we do this intentionally to avoid rearrangements. What we're really seeing is this, and there's a slight positive charge on the more substituted carbon because carbocation would be more stable if it's more substituted. So because of that, water substitute directly at that more substituted position. With this, just like last time, the water needs to be deprotonated to turn it into an alcohol. But instead of using another water molecule, we use the most basic thing in the solution, which in this case is that acetate ion left over from the beginning. So that finishes that off. And we still have this mercury, but that's why we have the second step with sodium borohydride. All that does is it just gets rid of the mercury and it replaces it with a hydrogen. So then it just leaves you with this as your solution. Okay, so both of those left you with the more substituted solution, the Markovnikov solution. But what if we wanted this? What if we wanted the less substituted alcohol? In those cases, we use a different reaction called hydroboration oxidation. Pretty much all you need to know about this is that you end up with the less substituted alcohol. I'm going to go over the mechanism just like the other two if you want to see that, but feel free to skip ahead if you feel comfortable with it. My bad. Quick note. This is broken up into two steps also, just like oxymercuration. This mechanism is quick because it's two steps, but you only really need to understand the first one, and then the second step is more of a conceptual understanding that you're going to need. This works because the boron will go to the less substituted side, and these two movements will happen at the same time. This will happen 3 times around one boron, and with each of the hydrogens. So for one boron, this will happen 3 times, and then you'll have pretty much this complex where it's almost in a circle around the boron. And then just like the last reaction, the second step of the reaction just replaces the boron with what you need. So in this case, it replaces the boron with the OH group, and you'll end up with the alcohol, like so. Okay, so quick recap before we move on to practice problems. What we should have gotten away from those mechanisms, pretty much if you're going into a test, deep understanding is important, but if you need quick tips, just know that hydration is Markovnikov and it has a cation, a carbocation, so it can allow for rearrangements. Oxymercuration is Markovnikov, but there's no carbocation, so there are no rearrangements. And hydroboration is anti-Markovnikov. By Markovnikov, I mean that the oxygen or the alcohol, the OH, will end up on the more substituted carbon. By that I mean if you have like this, this is secondary, this is primary. So in a Markovnikov solution, ends up there as opposed to here. Just take those tools and we're going to jump into practice problems. I'm going to give you them in the format that you might get them on a test. Pause, try it. We'll come back and see how you do. Okay, try this one. Pause, I'll get back to you. Okay, so the answers to this one, I say answers in plural because there are two, are these. They end up showing up in equal amounts, and I'll show you why right now. Remember, hydration creates a carbocation, and it's Markovnikov, so it'll end up on the more substituted side. However, in this case, both sides of the double bond are secondary, so it'll end up on either side equally. And those show up in a 50-50 ratio. Now remember that carbocations can rearrange. This one is done because rearrangements can only happen to adjacent carbons. And this carbon, this carbon, and this carbon are all equally substituted, so the cation is equally supported or stabilized. So it has no reason to rearrange. But with this one, we have some work to do, but just a little bit, one step one. There's a hydrogen here that does a hydride shift, which moves the cation over. And then the water just fills in to where the cation is. And don't forget to deprotonate. There it is. So you have that, and you have as your final answers. Sure. Good job. Okay, what about this one? What happens when we do an oxymercuration reaction with this? Pretty straightforward. You just get the Markovnikov solution, but we did oxymercuration for a reason. We're gonna have some more moving parts when we do this. Try this. Okay, so the answer here is actually this. And I know it looks different, the whole thing changed. If you don't know why, we're gonna get to that right now. So the same thing that normally happens at first happens. The bond reacts with the hydronium ion, and you end up with a carbocation. But remember, carbocations allow for rearrangements, and that doesn't have to mean hydride shifts. What we just saw was called a ring expansion. It happens because at certain angles, there's more strain on the bonds of carbon rings. Pretty much a rule of thumb is that they want to be cyclohexane. They want to have 6 carbon rings. So 6 is more stable than 5, and 5 is more stable than 4, and so on. So in this case, we have a 6 carbon ring and a 4 carbon ring, and the 4 carbon ring is very unstable. So what happens is ring expansion. These electrons move out this way, and then that will turn into this, and the cation is here. If you're having trouble seeing this, it can be hard to visualize. What you can do is you can count the carbons. So 2, 3, 4, 5, 6, 7, 8. Okay. Now, as that moves, the the electrons between carbon 8 and 6 moved over to where carbon 1 was. So I'm going to number off the carbons over here so you can see what this looks like. So this is where the carbons moved. The the electrons between uh, carbons 5 and 6 here flapped open, and now 5 is bonded. Carbon 5 is bonded to carbon 1 here. So you have 2 5s. And that is this is a more stable structure than this was. By the way, professors love throwing these into exams because it means that you have to pay like very close attention and understand what's really happening with the rearrangements. So be on the lookout for this on exams. Now to handle where the cation ends up, we see here, this carbon has 4 bonds. This carbon has 3. So this carbon has a positive charge because it's missing a pair of electrons, where this one has all of its electrons. But the electrons from here moved here. So in the end, this carbon is going to be missing electrons, and this carbon is going to have those electrons. So this one this one, my bad, will be neutral, and this one will have a positive charge, which is why we end up with this. The water ends up going to the same spot, but not the same spot, the cation again, and then we deprotonate, and in the end, like all that stuff happens, and in the end you end up with this alcohol. Done. Okay, new problem, try this, give it a go. I'll get back. Okay, this one is weird because there's technically 2 answers. You should know that there are 2 solutions that can end up with this alcohol, but only one of them will give you this alcohol 100% of the time. Here's what I mean. Hydroboration has anti-Markovnikov tendencies. So we're taking an alkene, meaning there's a double bond somewhere on this, and we need this carbon to be the less substituted of the 2 on either side of the double bond. We can look around. This is a secondary carbon. This is also secondary carbon, but this is a tertiary carbon. So we know that if we draw a double bond here with hydroboration, the alcohol will always end up on the secondary carbon because it's less substituted. So this answer works 100% of the time. You always get the right alcohol. But remember, there are two answers, and the second one only gives you the right answer 50% of the time. That is because this is the second answer. And as you can tell, both of these carbons are secondary. They both are attached to two other carbons. So this can give you two different answers in 50-50 ratio. That's these two. Um, this one, this one is something that happens when we do this, but it's not what was asked in the question. This is the end material we're looking for. So on an exam, this will technically give you the right answer, but the other solution gives you the right answer 100% of the time. So if you're asked a question like this, go with the other one. Okay, this is a similar problem. Um, what starting material, what alkene, will give you this alcohol through oxymercuration? Give it a go. So again, this has two solutions, two places in which you can place the double bond that will lead to this being the more substituted carbon. This is one of them, and you'll always get the right answer with this. What's the other one? It might be harder to see. Okay, so we're going to draw the double bond right here. So you're going to end up with the more substituted bond being this, and you'll end up with that alcohol. Okay, this is another problem in a different format this time. Tell me the reagents you'd use to turn this alkene into this alcohol. Hydroboration. Because, simply put, this carbon is tertiary, this carbon is secondary, this carbon is quaternary. So with the double bond here, you have a tertiary carbon, a secondary carbon. You need to go to the less substituted side. If you use oxymercuration, you're going to end up here, and you're going to have the same place with a hydration. So the right answer is hydroboration. BH3 and THF, and then sodium hydroxide, hydrogen peroxide, and water is the second step. Okay, here's the last question. Sometimes on exams, professors will write an entire reaction for you and ask you to explain it using a mechanism. So here, I want you to propose a mechanism for this reaction. How does this alkene, through hydration, results in this alcohol, given what we know? Okay, here we go. So the right answer goes like this. I'm just going to write it out and show you, and then I'll explain it after. We have a ring expansion. Okay, now after the ring expansion, you may be tempted to uh, attack that cation with the water, but this is where people get messed up, is because this carbon is more substituted than the other. So we have hydride shift. And then the water can attack. And as always, do not forget to deprotonate. So this there. And that's your final solution.